Okay, so let's define the Gaussian state again and then try to derive its general form. Okay, for us as usual, H is L2 of R, which we are identifying with gamma of Cn. And we have Weyl operators, and we have E minus I T P of alpha equal to W of alpha. These are all Weyl operators where alpha is in Cn. So we know all these things. And the definition is, we know the definition. The definition, rho on L2 of R, Rn is Gaussian, is a Gaussian state. A state rho on R L2 of Rn is Gaussian state if P of alpha follows normal with respect to rho. Okay, this rho, I mean, this rho gives rise to a distribution on the spectrum of P of alpha, and that is supposed to be normal distribution. Then we call it Gaussian distribution for all alpha in Cn. Okay. So this is equivalent to saying, P of T alpha, P of T alpha. Whatever we have defined as the quantum characteristic function, and rho of T alpha for all T, rho of T alpha for a fixed, see, P alpha follows normal, okay? Then rho hat of T alpha equal to, which is see, suppose mu is the distribution. Mu is the distribution induced by rho on the spectrum of P of alpha. Okay. Then integral over integral over R, let's say R, E of minus I T P of S d mu S. Okay. This is actually equal to trace of e power minus it p alpha, okay, rho, right? This is equal to this. And that is Gaussian, means since Gaussian, that has to look like e power minus I t some m. Okay, this m will depend on alpha. Okay, minus half sigma, which depends on alpha, again, t square, right? Sigma t square. That is how it should look like. Okay, this is for all t. This is arbitrary alpha, but which is fixed here. So this is for all t in R. Okay. Now this left hand side, this right hand side is a analytic function, which is infinitely differentiable function, which is e power something, which is infinitely differentiable function. And so you can differentiate the left hand side also or the right hand side also. You can either do that or you can expand the power series, whatever you can do. So by differentiating and evaluating a t equal to 0, you find that this trace of P alpha rho, this is what is the mean of that. Okay, T alpha, this is equal to m of alpha. You'll find it. Just differentiate both sides. Differentiate both sides with respect to t. Okay, there will be a t square term will give something when you evaluate t equal to 0, it will vanish. Okay, so you will only get m alpha when you differentiate once and evaluate t equal to 0. You will get m alpha, possibly minus m alpha, and there will be minus there also. So this is trace p alpha. The trace of p alpha rho is equal to m alpha. So this is one thing you get. Then differentiating twice. Once at t equals 0, and again differentiating twice twice at t equals 0. We again get the trace of p alpha square rho, okay, minus m of alpha. You will get a minus m of alpha equal to half sigma of alpha. Okay? That's what you will get. So you call it 1, you call it 2. Okay. So, okay, now notice, I mean, this you have to notice in the differentiation. Alpha going to P alpha is real linear. It's not complex linear. If you want, you should know that the annihilation operator is conjugate linear and the creation operators is complex linear. Okay, this P alpha is actually a linear combination of annihilation operator and annihilation operator, creation operator, we defined as P of alpha minus I times P of I alpha. Okay, that's how we define. Okay, so that is annihilation operator, and if you take plus in the middle, then that is creation operator, one of them. Okay, so they are, one of them is linear, another one is one of them is complex linear, another one is conjugate linear, but the anti-linear, whatever you want to call it. So this P alpha is a combination of those two things. So it cannot be linear, complex linear. It is only real linear, but that is enough. We only want that. Okay. So this P alpha is real linear. So in particular, this map, whatever we have. So in particular, this says that alpha going to M alpha, which is a real number. Of course, this is an R, of course, is real linear. Okay. So this implies M alpha is equal to, we get some number. L, M, alpha is equal to x plus iy, let's say. XY, where LM is in R2 power n and alpha equal to x plus iy. Okay. Clear? Freeze lemma. I mean, it's anyway finite dimensional. You don't need all that. This is only finite dimensional. You need dual is given. You know it's dual exactly. Okay. So, and this is how M alpha will be a functional, evaluated. Yeah, when the LM is in the right place, correct. Yeah, because we want it real. So, our inner product is linear in the second variable. So, this is okay. This anyway doesn't matter. This is a real inner product. Sorry. This is only real inner product, not conjugate. This is an R2n. So, it doesn't matter wherever you write. Okay. So we got this. So one thing is we have got a form for M alpha. M alpha is actually given by one single vector. Okay. On the other hand, this map alpha beta going to be, where alpha equal to, let us say, x plus alpha beta going to be let's say alpha and beta, I want to write it as alpha equal to x plus iy and beta equal to x prime plus iy prime, let's say. Okay. Going to this half trace of P of alpha minus M of alpha, okay, rho, and P of beta, maybe I can write it together, doesn't matter. P of beta minus M of beta times rho, plus, because because this is not, you can't interchange these two things. You can't interchange alpha and beta here. Okay. So I have to write it as trace P of beta minus M of beta. This is what is called covariance, okay, between P of alpha and P of beta. Okay, and P of alpha minus M of alpha. So P of alpha is an operator, M of alpha is a number, okay, just a scalar, M of alpha times identity. Okay, that's what it means, times rho. This is just the expectation of that product. That is the expectation of the product. And this is what is called the covariance. Okay? This is what is called covariance. I mean, P of alpha is one random variable. P of beta is another random variable. This is the covariance between those two random variables. They are non-commutative, and this is the covariance between them. Okay, you consider this. This is a bilinear map. Okay, real bilinear map. This map is real bilinear. Okay. This map alpha going to the covariance of P of alpha. I mean, this is just the covariance of P of alpha, P of beta. Okay. So alpha beta going to this covariance of P of alpha beta is a bilinear map. So it's given by a matrix, of course. Okay. It's given by a matrix. So in particular, our sigma, whatever the sigma we have there, okay, there what we have is, so given by a, I mean, so given by a R2n, I mean, 2n cross 2n. This is alpha and beta, they are all, I mean, they are alpha and beta. I mean, when you write it as consider as x plus xy as real vector space, is 2 power n dimensional. 2 power n cross 2 power n real matrix. Okay. Yes. Okay. So, and our sigma is nothing but whatever we have, half sigma alpha is nothing but alpha S alpha. The covariance between P of alpha and P of alpha is the variance. Okay.
So could you scroll up a bit?
Yeah, I'm scrolling up.
Yeah.
So the mean is clear, no? Mean just gives a linear map, so it is given by something. That is clear. Okay. So the next thing is I'm taking alpha beta, taking to the covariance of P of alpha, P of beta. That is a matrix. That's bilinear, so it's a matrix. Right? So alpha, so this is a matrix. Okay. And it's given by a matrix. And so if you take alpha equal to beta, that is precisely what we have here. P of alpha, see, you just write it. That is precisely the variance. If you want, you can take the M alpha inside. Okay. So it will, I mean, trace row is 1. Okay. Which will be P of alpha minus 1 whole square you will get. I mean, you can write it. I mean, you know the variance formula. You should have studied in statistics. Variance is equal to, I mean, you can write it as, yeah, x minus the mean of that. It is the expectation of x minus x bar whole square. Or it can write it in the other way also. Okay? There are two ways of writing the variance. So if you use that, this is precisely the variance. Okay. So this implies half sigma alpha equal to this. Further, this is a, I mean, P of alpha, P of beta. This is clearly, I mean.
So it should be something like M of alpha square.
M of alpha? Exactly, correct. You are right. Good. It's M of alpha square. Yeah. There we should have M of alpha square, correct. Yeah, that is what we will get. I didn't really differentiate, I just said it. That's the mistake. Yeah, correct. It's M of alpha square. Then only it will be correct. Yeah. Right? So we got this. So S is also symmetric, as you can see. Covariance of P of alpha, P of beta is P of beta, P of alpha, from the whatever the formula we have written. So this implies S is symmetric, S is equal to S transpose, and S is positive. And this is greater than or equal to 0. So this implies S is positive. Okay. By positive, we mean it's at S alpha is greater than 0 and S is symmetric. Okay. S is positive. So we got a positive matrix. So this thing implies, all these things imply rho hat of alpha is equal to exponential minus I. So which is I take the inner product. Inner product x xy or lm here, no? lm x y, okay, minus half alpha is alpha. I should write it as xy. Okay. So this is the form. Okay. This S is called the covariance matrix, covariance of rho, and Lm we can call the L plus Im, the mean. Okay. Or you can take the Lm vector also, doesn't matter. Okay. You can call it whichever, which is the mean of rho. Okay. So we have shown that this is exactly similar to the n-dimensional, two n-dimensional Gaussian, I mean, the classical Gaussian random variable, Gaussian measure. It's just the character. It exactly looks like that, except that you will not get all S. Here it's complex. Rho, it's complex. But if you consider as a 2 power n, I mean, it's considered as a alpha in R2n, then it is just the R2n Gaussian random variable. Okay. So this is just the characteristic function of that. So we get exactly that. Okay. But then there is some more condition. That's what we want to see. Now we want to see that what are all the possible. So what should I do? So what are all the possible value of S? We have already seen that S can be identity and the mean can be anything we want. So let's just make the remark. Let us observe the remark. Okay. If rho is a Gaussian state with mean 0 and covariance yes, then W of alpha yeah, imaginary part of it, W of alpha rho W of alpha star. So you will get 2 power minus is a so you will get 2 I know. So this is a is a Gaussian state with mean 2 alpha or minus 2 alpha. I'm not sure. Okay, plus or minus 2 alpha. Okay, it's just plus or minus 2 alpha. It will just multiply. We have already seen this. Okay, 2 alpha and covariance. Yes, we have already seen this. If we conjugate with W of alpha, W of alpha, then the characteristic function will be multiplied by e power 2i imaginary part of alpha times whatever that variable in the Gaussian thing. So which will just you will get which will just shift the mean. Okay, so if that is the Gaussian with 0, then we will get the mean with so 2 alpha will give all mean, right? I mean, we'll get, so if you have got a Gaussian state with mean 0 and covariance yes, then we can all get for any alpha, we can get a Gaussian state with mean alpha and covariance yes. Okay, we can get that. Okay, so only our problem is to see what are all the covariance yes, and this is something which is, I mean, which should be normal. I mean, which is expected, because we get all mean. That's not a problem. But there is only restriction is uncertainty principle. So which is a restriction on the variance, which is a restriction on the covariance. So that's what we should see. Okay. Okay. So this is so we are only worried about Gaussian state with mean 0. Okay, that's what we will worry about now. Okay. Okay. You just see it. Okay. So let us try to get Gaussian random variables with I mean, what are all the possible? So first I want to say that in two cross two situation, I mean, when n equal to 1, okay, assume n equal to 1 now. Okay. We will come to other properties later. Okay, assume n equal to 1. Okay. Then I want to say that if the determinant of S is greater than or equal to 1, okay, then I get all possible Gaussian state. I mean, all possible Gaussian. I mean, I get a Gaussian state with covariance matrix S with determinant of S equal to 1. Okay. So we have already seen that if L is a symplectic, I mean, this is something general. We know that if L is symplectic, then gamma of L, rho gamma of
I think one of my friends will have a charger, but I asked him.
there is 10%. So
Okay, fine. If it's last time.
yeah, let's see how much time it goes. We will have a longer session next time. Okay. Gamma of L, gamma of star, gamma of L inverse hat, which is going to be at alpha, at Z or whatever, equal to rho hat of L inverse Z, right? Okay. So if rho has mean 0, let's not worry about mean. We assume that mean is 0, okay, from here onwards. Okay. Suppose rho has covariance. Covariance, yes. Okay. Then gamma of L, rho, gamma of L inverse has covariance. You can just see it will be L inverse Z will come. I mean, it is just, you will have only this alpha, S alpha, and here you will get gamma, I mean, L inverse, and you will get L inverse. Sorry, you will get the L inverse here inside. L inverse alpha, right? Inside the Gaussian, I mean, the characteristic function. So this will have covariance L inverse transpose, okay, yes, L inverse. Okay. So in particular, if L inverse is positive, or I mean, if it is L inverse transpose, right? You'll get L inverse here, and L inverse transpose, correct? Okay. So if L is positive, then we will get L inverse itself. Okay.
Why do you think positive means selectively?
No, symplectic can be positive.
That's why do we need positive?
No, we don't need. If it is positive, we'll get L inverse transpose is L inverse itself. I'm just saying. What I'm saying is, if S is identity, so in particular, if S is identity,
So it's symmetric would be enough. Like symmetric is.
That's fine. Okay, but I mean, I want positive matrix, no? So I want to. If S is equal to, then I have to take the I mean, I want positive matrix, right? So
Covariance is positive. Right?
Covariance is always positive. So it should turn out to be positive somehow. Okay. I mean, there is, I mean, still you may get positive. But,
no, like then L can still be symmetric.
Correct.
It will still be positive.
Yeah, it may be, yeah. I mean, but anyway, we want to get the all examples. And if suppose determinant of L equal to 1. Okay, let's assume N equal to 2. Okay, N equal to 2. Okay. Determinant of L equal to 1. Then L will look like some, I mean, some number and its inverse, right? That will be its eigenvalues. Okay, L will have eigenvalues. So L is equal to, L will look like some, but there will be a unitary there. Yeah. Then L will look like some unitary times lambda, lambda inverse, right? Some U star, right? Because that will be the identity. That will be the. So if we have any determinant of L equal to 1, any matrix with determinant of L is equal to 1, with any, I mean, then L is automatically symplectic. That's what I'm saying. This lambda, lambda inverse is symplectic, of course. Then of unitaries are symplectic. So it's okay. This is symplectic. Okay. Then L is symplectic. Okay. And L inverse. So if we take, I mean, if we replace L by L inverse, I mean, if we say S is identity, then rho hat gamma of L power minus half gamma of L power minus half will have I mean,
Previously we are assuming L is positive.
yeah, L is positive, yeah. Okay, so then it has covariance matrix L, right? And if L has determinant 1, okay, if I mean n equal to 1, not 2, n equal to 1, so 2, I mean the matrix are in, we are the matrix is in 2n, okay, n equal to 1, okay. So if S equal to identity and determinant of L equal to 1, then L will look like that. So it is automatically symplectic. Okay, it's automatically symplectic. Okay. So gamma L minus half, rho hat, gamma L minus half will have covariance L. Okay. So we get, so if we we get all covariance matrix with determinant equal to 1 as Gaussian state. Okay. I mean, we get all covariance matrix with determinant 1 as covariance matrix. I mean, all matrix with determinant 1 as a covariance matrix of the Gaussian state. Okay. I think it is the right statement. Okay. Yeah. Okay. So that we have. Now we want to get it for determinant greater than 1. Okay. And that is expected because only when the covariance is very less, I mean, covariance is near 0 or something greater than some 1/4 or something. It will be 1/4 in our case. I mean, it should be determined by Planck constant. But in mathematics, Planck constant is 1. Okay. So, so it will be nearly, I mean, this less than 1 only, we should, I mean, there will be some problem. Okay. So when the covariance is bigger, there shouldn't be any problem. I mean, we should have such states. Okay. So what is the statement? So suppose, so the next case is determinant of some matrix, determinant of S is greater than 1. Okay. Determinant of S is greater than 1. Then S is equal to, S will look like what? S is equal to determinant of S power 1 by n, right? 1 by n into determinant of A. I mean, S is equal to times A where determinant of A equal to 1. Okay. Correct. Okay. This is a constant, it will have lambda power n. That will be the determinant. Okay. So now A has determinant, A is a positive matrix and S is greater than 0. Okay. And A has determinant equal to 1. Okay. So this determinant S is greater than 1. So, okay. Now consider this state, rho S is equal to 1 minus e power minus S, e power minus S, A dagger A. Okay. We have already seen this. Okay. Then we know that rho hat of S is equal to rho hat of S at alpha equal to e power minus half cot h S by 2, okay, mod alpha square, right? I think this is the right statement. Okay.
Yeah, square.
What square? I think it's just cot h square. Okay. I think last time I made a mistake. I didn't calculate. I gave it as an exercise. So, what does it say? Yeah, minus half cot h is by 2, right? Yeah, there is no square. Okay. So last time it was a mistake. I didn't make a mistake. I said it the wrong. I made the wrong statement. Okay. Yeah, it is cot h is by 2. Okay. Okay. So now here the covariance matrix is so rho hat. I mean the covariance of rho s is equal to cot h s by 2 times identity, right? Okay, and the determinant is, I mean, we know that, I mean, determinant is something greater. This is greater than 1. S is greater than 0. This is greater than 0. This is greater than 0. Okay, then this will take the value between 1 to infinity. Okay, so S can be written. So now we have a matrix with determinant A equal to 1. So if we have a positive matrix with determinant A equal to 1, so S is equal to, I mean, we have a S, we want to get it, I mean, we have a, sorry, I should have written it in small letters. So we have a S with determinant S greater than 1. Then S is equal to cot H S by 2 into something about of, it's like this. Cos theta minus sin theta. I will tell you how you get it. Sin theta cos theta. Okay. Times e power t, e power minus t. 0, 0. Okay. E power t or lambda inverse. It's okay. I don't see why e power t is needed. But lambda should be positive. Okay. So that's why e power t. Okay. Then cos theta sin theta minus sin theta. This is what is called rotation matrix. This is nothing but if you take a complex number z, multiply by e power I theta, which is a rotation, okay, in the complex plane, which is exactly given by this matrix. If you consider in R2, okay, it's exactly that. Okay. So this is how any S will look like. Reason, if you have any S, it will look, so if you have any unitary matrix, okay, then its determinant will be of modulus 1. Okay. So you can take the modulus, you can write that unitary matrix as some matrix, I mean, some matrix is determinant 1 times some Z, which mod Z equal to 1. Any unitary matrix, even in complex plane. But then that by in conjugation, you can take out that whatever. I mean, even in C2, this is true. Okay. So in R2, you can write it as the conjugation by rotation and something like that. Okay. That is the eigenvalue, and this is just the rotation.
That's e power t, e power minus t.
Yeah. E power t, this is 0. Okay. Lambda inverse, but it has to be positive, so it's written as e power t. Okay. Okay. So any matrix will look like that. So how to get the covariance matrix? So now, so you define, let rho s theta, rho s t theta, okay, equal to gamma of L power minus of, let's put minus of rho s let me tell you LT minus half rho s gamma of LT minus half. Okay. Then gamma of e power I theta, which is just the rotation. Okay. E power I theta as a complex matrix, it is just multiplication by e power I theta. which is that if you write it as 2 cross 2 matrix, it is that matrix. Okay. Gamma of e power minus I theta. Okay. We take this. Okay. So I say that this is this precise, then rho hat of st theta, covariance of this. Equal to e power minus half cot h s by 2 into, and LT inverse, LT minus half, LT minus half, and it will be the inverse there. So you will get the L there. Okay. LT will get, where LT is, I mean, LT equal to e power t 0 0 e power minus t. Okay. So you get the LT there. Now the point is, you conjugate this LT with e power I theta, but then you have to conjugate twice. If you want, you can take, I mean, you can insert a gamma e power I theta here, and it's star, which is identity, and you can do it here. But then conjugating rho s by any unitaries does not change anything, right? If you rho s, the characteristic, the covariance is given by I. Okay. If you conjugate a rho s by a unitary, it will not do anything because you have identity u star u will be 1. Right? So you will not get anything. I mean, by conjugating by a unitary, you will not get anything. So just check. Okay. So only by gamma LT will get. So this will be precisely gamma LT, and then this is the, I mean, I write it as u theta LT u theta star. Okay. Where u theta equal to the rotation matrix. Cos theta minus sin theta, sin theta, cos theta. Okay, which is just the rotation. Is it clear? Did I mess it up? You take rho s, which has the characteristic function cot h s by 2 times identity. Okay. So if you first conjugate by gamma of L power minus half, okay, you will get the L in the space, in the place of I. Okay. Now you conjugate with e power I theta, the rotation matrix or the rotation matrix. Then that will get conjugated by, maybe you conjugate it twice. I mean, conjugate the rho s before that, and then, I mean, maybe you consider this. What I'm saying is, this is actually equal to rho s gamma of e power I theta gamma of e power I theta rho s gamma of e power I theta gamma of e power, and here it's e power I theta, here minus e power I theta. Okay. Then gamma of e power I theta L gamma of L power minus half actually the homomorphism property is not needed. Like that is needed. That's not needed, because once you conjugate it, you will get the unitary inside. Okay, that's not needed. Here I can again gamma e power I theta.
The conjugating one should be in.
Huh?
Why are you doing?
That is because I want to conjugate. I want to get the conjugation of L there inside. If you conjugate a state, you will get a L inside. I want to get a conjugate of L by the e power I theta. So I have to conjugate. I have to write it like this.
Okay, yeah.
But then this does not really change anything. Okay. So please do the exercise, and you will get that. Okay. That's what I'm saying. Okay. Here I have written UT, LT, UT star. Okay. So I have written gamma of e power I theta, gamma of LT power minus half rho s. So you can conjugate the rho s also again by gamma e power I theta, and I want to get the conjugate of gamma of LT power minus half inside, right? Gamma of LT, right?
Yeah, but like if you work through it, it will become identity, right? Like the first conjugation you do on the inside, like you said, you are conjugating by unity. So it will anyway become this.
Yeah, it will become. How will it become by identity?
Because like you'll have gamma phi per I theta on either
No,
side.
no. First, if you apply rho s and you have an e power I, yeah, that will be rho s will not affect.
Yeah, it will be the same. So this should also be.
Correct. This should work. But anyway, yeah. Okay, yeah, this will work. Yeah. Anyway, so for any matrix with determinant s greater than 1, we have a Gaussian state with that corresponding covariance matrix. Okay. So that is clear. Okay. So next we want to determine the condition. So greater than 1 is not a problem. So less than 1, we want to see what we can get. Okay. So for that, I state the following theorem. This is the main theorem. Okay. F of s, f of alpha equal to, I don't care about the mean. Okay, we know that with all mean we get a Gaussian state. So I only worry about this. F of s equal to alpha minus half. I keep the minus half here. Okay, s alpha. Okay, s greater than 0. Okay, then is a characteristic function of a Gaussian state. If and only if, see, this is something tricky. This is something I don't really happy about it. See, something like this. S minus I times this matrix. I times the J matrix we have written now. S minus Ij is greater than or equal to 0. What it means is the following. See, S is a real matrix. It's acting on R power 2n, R2n. J is a real matrix on R2n. So you are multiplying by I. Okay, so it's a kind of complex matrix. Still, it can act on real thing. Okay. This
is all one matrix.
Huh?
What is G?
One off diagonal 1, 1. J is this. J is equal. We define J. J is equal to 0 minus 1, 1.
So in another course, there's J.
Okay, yeah. Yeah, this is J. J comes in many places. Yeah. So, yeah, we know that imaginary part of UV is equal to UJV. Okay. That is the importance of J. Okay. So keep the battery. If when it becomes 1%, I will stop. Okay. It's showing 4%. Okay. So this is what I want to prove. Okay, proof. So before this, I need something that's something about the positive definite kernels. Okay. So this which I will prove in the next class. Which anyway we need. We may not need it again in this course, but in any way, when you do quantum probability, it's better to know about these positive definite kernels and other things. So we will anyway do it. Okay, it's just for this theorem. So this is the proposition. Okay. fact. So suppose kt from see, there is something called semigroup of positive definite kernel. This is a function from okay, let's take Rn itself. Okay, we have only Rn cross Rn to C. Okay, this function from Cn to Cn. No? Okay, Cn to Cn. C. Be a semigroup. The fact is the following are equivalent. Kt be a semigroup of 1. Kt is a semigroup. B is a semigroup of positive definite kernels. What it means is each Kt, I mean, is a continuous, is a semigroup of continuous positive definite kernel. Kt is continuous. Of course, continuous means continuous on the metric space Cn. And each Kt is positive definite. We know the definition. Okay. And further, Ks times Kt, just the product. These are all functions. Just take the product, which is Ks plus T. Okay. This is what's in. Okay. This is for T greater than or equal to 0. Okay. So that's why it's semi-group. Otherwise, it will be called a group. If we allow T negative, it's called group. Okay. So, okay. This is equivalent to saying we don't need that fact. I will not prove it in this generality. So, I mean, this is what is called infinitely divisible positive definite kernels. So I can have a particular form for this because we have a particular form. So I'm sorry, I will erase this. This is more general. We don't need it. We assume that it is in the form of e power t. Okay. We write the log explicitly. The following are equivalent. The first statement is kt xy equal to e power t lxy. Okay. L is a function. Okay. I mean, it's continuous. E power t is continuous. So it's a continuous. It's continuous in lxy. So I should need continuous. Continuous positive definite kernel on Cn. Okay. On Cn cross Cn. Okay. Cn. It's clearly a semi-group. I don't have to write it. Okay. T greater than 0. Okay. Then that is equivalent to saying Lxy is conditionally positive definite. I will write the meaning of it. Conditionally positive definite. Meaning that is summation lambda I bar lambda j. Okay. L of xi xj, okay, is greater than or equal to 0 for all summation lambda I equal to 1 to say n is somewhere, so k equal to 0. Under this condition, it is greater than 0. Without this condition means it's always positive. Okay. This is what is called conditionally positive definite. This L is the log of the positive definite function kt. Okay. So if kt is positive definite for all t, then this is positive definite. This L is positive definite. Okay. The statement is more general, but I will just use this. Okay. This is positive definite. So this is equivalent to saying L of xy minus L of 0 y minus L of x0 plus L00, I think. Okay. Is positive definite. Okay. I mean, I remove the continuity. Continuous is not needed here. I mean, for this equivalence of statement, if that is continuous, this will be continuous. Okay. So this is positive definite. L of xy minus L of 0y, L of x0 plus L of 00 is positive definite. Okay, I want to use this. Okay. Okay, we'll stop. We will use this and we'll do it next time. I think I won't be able to finish the proposition today. Okay, anyway, so I don't want to leave it in the middle. We'll do it on Friday. But I want to say the following. Okay. So, see if A is a matrix, A is in M, N, R, okay? Then define A hat in M, N, C by A hat of x plus I, just the AX plus I, AY, okay? Which you can define, okay? So now this is what I want to make the remark. Because I really not happy with this statement. See, S minus Ij is greater than 0. I want to write it in the complex as a complex statement, which will be clear. Okay? The Ij is symmetric. J is not. J is antisymmetric. So J is antisymmetric. So Ij is symmetric. Because I means you will get a minus sign. So in the complex case, okay, the star is not the transpose is minus, but if you take the star, then it is actually symmetric. Okay, so we are comfortable with the complex space. Okay, so S minus Ij if xy S minus Ij. This is just xy. Okay, this is greater than or equal to 0. Okay, is equivalent to saying S minus Ij hat is positive as an element, in M2NC, okay, as a C2N cross C2N matrix. Okay, so this statement, then we don't have to worry about what carries over or something. I mean, we can use the positive definite matrix, complex positive definite matrix. We have theorems we can directly apply. Okay. Okay. So this proof is clear. I mean, this is easy. We just have to, what do we have to do? So suppose if we have a S minus Ij hat, I want to take the inner product this way. Okay, leave it as an exercise, or I will check it next time. It's very easy. You just have to use the symmetric. I mean, this is symmetric. Just use the inner product. For complex thing, you don't have to verify anything, right? In the complex space, something is positive if xi. I mean, you don't have to worry about symmetricity and A xi is greater than or equal to 0. This is the condition for something to be positive, which you can take any C2n vector, you write it as that and apply the definition, you will get it. Okay. So I leave this as an exercise. exercise. Okay? It will work.